Hey everyone, and welcome to The Explainer. Today, we're going to tackle a concept that's, well, it's a cornerstone of computer science. It's incredibly powerful, and yeah, it's going to bend your mind just a little bit. We're talking about recursion.
All right, let's kick things off with a question that might sound a little strange. What if a function, a block of code that does one specific job, could actually call itself to get that job done? It sounds like a loop or maybe a paradox, but it's really the key to cracking open some seriously tough problems with code that's, well, surprisingly elegant.
Okay, so let's get the official textbook definition out of the way first. Recursion is when a function calls itself to solve a smaller piece of the exact same puzzle. And it keeps doing this, breaking the problem down again and again and again until it gets to a version of the problem that's so tiny, so simple, it can be solved instantly without having to call itself anymore. To really wrap our heads around this, we're going to use the classic factorial example. And hey, don't worry about the math, that's not the point here. I want you to think of it more like a story, a countdown really. It's a journey down to one simple, known answer that's going to unlock the whole thing.
So, picture this. You ask a function, hey, what's 5 factorial? The function goes, okay, I can do that, but hold on. To tell you that, I first need to know what 4 factorial is. So it calls itself to find out. And that new call says, sure, but I need to know 3 factorial first. And you see what's happening? We get this chain reaction, this waterfall of questions, each one a little simpler than the last, all the way down the line.
So we've gone all the way down the rabbit hole. We've asked question after question, all the way down to the simplest possible one. So what is 0 factorial?
1. That's it. That's the answer. And this right here is the single most important part of the whole process. In recursion, we call this the base case. It's the bottom of the ladder. It's the anchor, the one solid piece of ground that stops the endless questions and finally gives us a real answer to work with.
And just like that, we can start climbing back out. Because we know for a fact that 0 factorial is 1, we can now answer the previous question. What's 1 factorial? Well, it's 1. And with that answer, boom, we can solve for 2 factorial. And we use that result to solve for 3 factorial. We're just climbing back up that ladder of questions, carrying the answer with us, until we finally get back to the top with the solution to our original problem. 5 factorial is 120.
Okay, so that's the idea, right? This cool concept of a countdown and then a climb back up with the answer. But what does this actually look like when you're writing code? How do you implement an idea like that?
Well, take a look at this. This little snippet of Java code is a perfect picture of our analogy. See that little if statement? The if n equals 0? That's our base case. That's the anchor, the hard-coded answer that stops the countdown. And the else part? That's the recursive step. It literally tells the computer the answer is the current number, n, times whatever answer you get from calling me again with a slightly smaller number. It's the countdown and the climb all in one beautiful little package.
All right, so we get the what and the how. We see the idea, we see the code. But now you're probably asking, is this actually a good way to do things? Is it fast? How much work is the computer really doing here?
Well, to figure that out, computer scientists use a tool called a recurrence equation. And I know, it looks a little scary and mathy, but trust me, the idea behind it is actually super straightforward. It's just a formal way of describing the work being done.
Let's just translate this into plain English, right? T of n is just the total time it takes to solve the whole big problem. T of n minus 1 is the time it takes to solve the next size down problem. And that little plus b, that's just the tiny bit of extra work we do at each step. In our case, just one simple multiplication. That's all it is. It's a performance tracker. Okay, let's shift gears for a second and look at a pro-level tool. Because for algorithms that are way more complex than our simple factorial example, ones that split the problem into multiple smaller pieces, there's a kind of amazing shortcut for analyzing them. It's called the master theorem.
So this is what its general form looks like. You can think of this thing as universal key, a lifesaver, for a whole class of algorithms called divide and conquer. And that's exactly what it sounds like. You take a big problem, you chop it up into a bunch of smaller identical problems, you solve those recursively, and then you stitch all the answers back together at the end.
This table really helps make sense of all the parts. That letter A, that's just asking how many new little problems are you making each time. The n over b part is, okay, And how much smaller is each new piece? Like, did you cut the problem in half? And finally, f of n. That's just the cost, the effort it takes to do all that chopping, and then to glue the final answers back together. The theorem just balances these three parts to give you a really quick read on the algorithm's efficiency.
Okay, so we've covered a lot. The concept, the code, even some pretty advanced analysis. So what's the big idea here? What's the one thing you really need to take away from all of this?
It boils down to this, right here. Recursion is not just some fancy coding technique. It's a whole strategy, a way of thinking about solving problems. It teaches you to look at something that seems massive and intimidating and think, okay, how can I break this down, and down, and down, until I hit a piece so small that I already know the answer?
And that really leads me to the final thought I want to leave you with. So forget about code for a minute. Just think about your own life, your own work. What's a big, messy problem that you're facing that maybe, just maybe, you could solve by breaking it down into smaller, simpler, identical pieces?